All right, let's pull back the curtain on artificial intelligence. In this explainer, we're going to walk through the entire life of a machine learning model, from a total blank slate all the way to a sophisticated decision maker. So, let's dive right in.
You hear it all the time, right? AI can learn. But what does that really mean? It's not magic, I promise. It's actually a super logical and honestly fascinating process. So that's the big question we're tackling today. What is actually going on inside that so-called black box?
Okay, so the whole journey starts with the most fundamental thing there is, data. Before a model can learn a single thing, we have to figure out how to translate our complex world into a language a computer can actually understand.
Just think about it for a second. How does a machine, a thing that only really gets logic and electricity, how does it process something as rich and, nuanced as a photo of your cat or a really sarcastic product review? The answer to that is kind of the first big secret of machine learning.
It's all just numbers. Yep, every single thing. That photo, it becomes a giant grid of numbers, each one representing the color of a single pixel. Text, that gets broken down too. Words get counted or assigned numerical codes. Spreadsheets, well, they're easy. They're already in the perfect format. And even something abstract, like the color red, can be turned into a simple string of zeros and ones. This whole process, it's the foundation for literally everything that comes next.
So the first key piece of jargon we need is a vector. But don't worry, the concept is super simple. The easiest way to think about it is just a single row in a spreadsheet. That's a vector. It represents one complete observation, like all the features of a single house for sale, or the vital signs of one patient.
Okay, so if a vector is just one row, what's the next logical step? Well, that's the matrix. And a matrix is just the entire spreadsheet. It's a whole grid of numbers, really just a bunch of vectors all stacked together. And this is how the model sees the entire dataset it's about to learn from, just one big block of numbers.
All right, our data is now in a language the machine can finally understand. So the model is ready to take its very first step, which is to make a completely uninformed, basically random guess.
Seriously, an untrained model knows absolutely nothing. It's like a brand new student on the very first day of class, before they've even opened the textbook. If you ask it to predict, say, a house price, its internal weights, think of those as the little knobs and dials it uses to make decisions, they're all just set to random values. So the answer it gives? Yeah, it's pretty much a wild guess. So let's look at a concrete example. The model spits out a guess. This house is worth $750,000. But we have the real data. We have what's called the ground truth, which shows it actually sold for $500,000. Oof, that's a pretty big error, right? The model is totally wrong. But here's the thing. Being wrong is actually the most important part of learning.
Okay, so the model made a guess, and we know it's wrong. Now we need a way to measure how wrong it is. The model needs some kind of feedback, kind of like getting a grade on a test. And this is where something called a loss function comes in. Just think of it as the teacher who's grading the model's homework. It's a mathematical formula, sure, but all it really does is take the model's prediction and the real answer, the ground truth, and it spits out a single number that represents the size of the error. And that number, we call it the loss.
And the rule here is really, really simple. A high loss value, that's bad. That means the model made a huge mistake. A low loss value, that's great. It means the model's guess was getting close to the real answer. The entire goal of training, really, is to get that loss value as close to zero as we possibly can. Now, what's really powerful is that we can actually choose how we grade the model. For example, there's something called mean squared error, or MSE. It literally squares the error, which means it really punishes big mistakes. It's super sensitive to outliers. But then you have mean absolute error, or MAE, which is different. It just takes the absolute difference, so it's a lot less bothered by a few wild predictions. You see, choosing the right loss function is absolutely crucial for shaping how the model learns.
So the model has its score. It has its loss value. It knows it messed up. What happens next? Well, now comes the study session, where it actually uses that feedback to get better. And this right here is the real heart of what we call learning.
Okay, so the most common way models learn is through an amazing little algorithm called gradient descent. And the best way to picture it is to think of a hiker trying to get to the bottom of a valley. The loss value, that's your altitude. Obviously, you want to get to the lowest point. So what does gradient descent do? It looks around, figures out which direction is downhill, and tells you, hey, take a small step that way.
In this whole process, it becomes a learning loop. It just keeps repeating. Step 1, make a prediction. Step 2, calculate the loss, the error. Step 3,
find the direction to reduce that loss. And step 4, adjust the model's internal weights. Then, you just do it all over again, and again, and again. Thousands, sometimes millions of times. And with every single cycle, that loss gets just a little bit smaller.
Now, a super important part of this is something called the learning rate. Think back to our hiker. The learning rate is just the size of the step she takes downhill. See, if the steps are too big, she might jump right over the bottom of the valley and end up on the other side. But if they're too small, well, it could take forever to get there. Finding that just right learning rate, that's one of the real fine arts of machine learning.
So after repeating that learning loop over and over countless times, something pretty amazing happens. The model isn't just guessing randomly anymore. It's trained. But its graduation, so to speak, comes with a pretty big challenge for us.
And there you have it. The model is trained. Its loss is as low as it can get, and those internal weights are now finely tuned. It can now take brand new data, stuff it has never seen before, and make incredibly accurate predictions. We're talking about anything from recommending your next favorite movie to helping a doctor spot early signs of a disease in a medical scan.
But here's the catch, a really big one. The model can give you the right answer, but it usually can't tell you why it's the right answer. And as this quote from MIT News points out, in high-stakes fields like medicine or self-driving cars, just getting the right prediction, well, it's not always enough. We have to be able to trust it. This exact problem has led to the rise of a whole new field, explainable AI, or XAI for short. And its entire goal is to build models that can explain their reasoning in a way that we humans can actually understand and verify. The idea is to finally turn that black box into a transparent one.
And make no mistake, this isn't just some academic exercise. Explainability is absolutely crucial. It's how we build trust in AI for life or death situations. It's how we double-check that the model's logic is actually sound. It's how we debug problems when things go wrong. And in more and more industries, it's actually becoming a legal requirement.
So there you have it, the life of a machine learning model. It's a journey, right? From seeing our world as just a bunch of numbers, to making a guess, getting graded, and then slowly, painstakingly learning from millions of its own mistakes. As we build these incredibly powerful tools, the next great challenge isn't just about making them more accurate. It's about making them understandable, transparent, and trustworthy. Which brings us to the big question. As our models get more powerful, how do we ensure they're also wise?